Hello there, and welcome to the Sleepy Science Channel. Tonight, we are turning our attention to one of the most extreme and fascinating ideas in science. Black holes are objects so dense that space and time themselves behave differently around them. They are places where familiar rules begin to bend, and where some of the deepest questions in science are still waiting for answers. Black holes sit at the crossroads of gravity, motion, light, and time. They shape galaxies, power brilliant cosmic displays, and leave subtle fingerprints that travel across the universe. They challenge intuition, yet follow precise laws. They are invisible, yet their influence can be seen from astonishing distances. And while they may seem distant and abstract, they play a central role in the story of how the universe evolves. From the harps of galaxies to the echoes of distant collisions, black holes connect the very large with the very small. They link the birth of stars with the fate of matter, and they offer rare glimpses into conditions that cannot be created anywhere else. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Allow your body to soften and your breathing to slow. And let your mind settle as we explore this remarkable corner of reality together. Let's begin. A black hole forms when a massive star collapses under its own gravity. Not every big star becomes one, and that is part of the drama. When a very massive star runs out of fuel, there is no longer enough outward pressure to hold up the core. Gravity takes over, and the collapse accelerates. In a fraction of a second, matter is squeezed to densities that defy ordinary experience. The outer layers may explode outward as a supernova, while the core keeps falling inward. If the remaining core is heavy enough, even the strongest known forces cannot stop the crush. What is left behind is not a hollow void. It is a compact object with so much mass packed so tightly that space-time curves inward around it, like a steep funnel made from the universe itself. Black holes do not pull harder than stars, unless you get very close. This surprises almost everyone at first, because the name makes them sound like cosmic vacuum cleaners. From far away, gravity depends mainly on mass and distance. If the Sun were replaced by a black hole of the same mass, Earth would keep orbiting in almost the same way. The difference appears when you approach. A normal star has a surface, so you cannot get arbitrarily close to its center. With a black hole, the mass is packed into a much smaller region, which lets you get close enough for gravity to change rapidly across short distances. That steep gradient is what makes the environment so dangerous. In other words, the real threat is not a stronger pull from afar. It is how fast the pull changes as you near it. The point of no return around a black hole is called the event horizon. It is not a wall, and it is not a glowing boundary. It is a location in space where the rules of escape change completely. Outside it, you can still aim a rocket outward and, in principle, leave. Inside it, every possible path forward leads deeper in, even if you fire engines at full power. The size of this boundary depends on the black hole's mass. For a black hole with the Sun's mass, the event horizon would be only a few kilometers across. For a supermassive one, it can be larger than the orbit of a planet. What makes it so strange is that you could drift across without feeling a sudden jolt. The change is not in your body. The change is in what the universe will allow next. Once something crosses the event horizon, it cannot come back out. This is not a matter of strength or stubbornness. It is a matter of direction. Near the horizon, space-time is curved so sharply that outward stops being a usable future. Light beams aimed outward still lose, which means no message, no signal, and no last-minute rescue can reach the outside world. Yet the experience depends on where you are watching from. To a distant observer, a falling object can appear to slow and fade as its light becomes redder and weaker. To the falling object, the crossing happens in a finite time, with no flashing sign that announces it. That mismatch is part of what makes black holes so haunting. They can hide a perfectly ordinary moment inside a boundary that seals off the rest of the universe. Black holes are invisible because light cannot escape from them. That invisibility does not mean they are undetectable. A black hole can reveal itself by what it does to its surroundings. Gas that spirals inward can heat up until it shines fiercely, often in X-rays, because gravity converts motion into heat so efficiently. Background starlight can be bent into arcs or rings when it passes near, because gravity curves the path of light. And when a black hole sits in front of a distant source, it can briefly magnify that source like a natural telescope. Even the darkness can have a shape. The region, while light is trapped into tight paths, creates a silhouette against the glow around it. So the black hole itself stays dark, but the universe nearby can become bright, distorted, and loud in radiation, all because of the same invisible grip. Scientists detect black holes by watching how nearby stars move. Gravity leaves a signature that is hard to fake. If you see a star whipping around an unseen point at tremendous speed, you can work backward and calculate how much mass must be hidden there. The most famous example is near the center of our own galaxy, where astronomers tracked individual stars over many years. One star in particular follows a tight, elongated orbit that brings it startlingly close to an invisible central object before it swings back out again. By measuring that orbit carefully, scientists can infer both the mass and the compactness of what the star is circling. If the hidden mass was spread out, the orbit would look different. The motion instead points to something extremely massive, packed into a very small region. It is a detective story written in starlight and patience. The center of the Milky Way contains a supermassive black hole. It is not close in everyday terms, yet it is close enough that we can study it in detail compared with many other galaxies. This object sits in the crowded region called the galactic center, where gas clouds, dust, and stars weave through a complicated gravitational environment. Most of the time it is relatively quiet, which is part of what makes it intriguing. A supermassive black hole does not need to be actively feeding to dominate its neighborhood. Its gravity helps organize the central cluster of stars, and it anchors the motion of material across a huge region. Astronomers gave it a name, Sagittarius A star, though it is not a star at all. When you look toward the constellation Sagittarius, you are looking roughly toward this hidden center. A dark object sits there, shaping the architecture of our galaxy. That central black hole has a mass millions of times larger than the Sun. That number is not a guess pulled from theory. It comes from watching those rapid stellar orbits and measuring how fast the stars move, especially near their closest approach. With that information, scientists can estimate the mass required to keep the stars bound in such tight tracks. The result is astonishing. Millions of suns worth of mass is packed into a region small enough to fit well inside our solar system. This is one of the clearest examples of how a black hole can be both enormous in mass and compact in size. It also reshapes how you picture density. You can have a mass that belongs to a star cluster, and yet it behaves as if it is concentrated into a single, dark point. That concentration is why the environment near the galactic center is so extreme. Some black holes are only a few times heavier than the Sun. These are often called stellar mass black holes, and they are born from individual stars rather than from entire galaxies. Their size can be surprisingly small compared with their mass, which makes their immediate surroundings intensely violent when they feed. In many cases, they are found in binary systems, paired with a normal star. Over time, gravity can pull gas from the companion star, forming a swirling stream that spirals inward. As that gas speeds up, it heats until it shines strongly, and it can flicker as the flow changes. That flicker becomes a clue. By studying how the companion star moves and how the radiation behaves, astronomers can infer an invisible partner with too much mass to be a neutron star. These black holes feel almost personal compared with supermassive ones. They live in star systems, they interact, and they change their neighborhood dramatically. Others are billions of times heavier than the Sun. These are the giants of the black hole family, and they usually live in the centers of large galaxies. Their mass is so huge that their event horizons can span distances comparable to the scale of planetary orbits. That scale changes the feel of the gravity nearby. Instead of tearing things apart immediately, a very massive black hole can allow matter to orbit in large, stable paths far from the horizon. Yet when these giants feed, they can become the engines behind active galaxies, lighting up their cores with enormous power. They also influence their surroundings over long timescales. The growth of a central black hole appears linked to the growth of the galaxy around it, as if the galaxy and its hidden core are in a long gravitational conversation. Even when they are quiet, their mass shapes the motion of stars across the galactic bulge. Stellar black holes form from the deaths of large stars. In the final stages of a massive star's life, the core becomes a kind of cosmic balancing act. Nuclear burning once provided pressure that pushed outward, but as fuel runs low, that support weakens. The core contracts, heats, and races through its last burning phases until it can no longer produce enough pressure to resist gravity. What happens next depends on the mass that remains in the core after the star sheds material and explodes. If the core is light enough, it can settle as a neutron star. If it is heavier, collapse continues past every known barrier. That is the moment a stellar black hole is born. It can begin as something only a few times the Sun's mass, yet it carries the aftermath of a star's entire history in its gravity, its spin, and its place in the galaxy. Supermassive black holes likely grew by merging and feeding over time. These objects are so huge that it is hard to imagine them forming in a single step. A leading picture is that they began as smaller seed black holes in the early universe, then gained mass through a long series of meals and collisions. Gas drifting toward the center of a young galaxy can settle into a dense, rotating flow that steadily feeds the central black hole. At the same time, galaxies collide and merge, and their central black holes can end up bound together in a slow, spiraling dance. Over millions of years, they lose energy and finally combine into one larger object. Each merger adds mass and can change the final spin. Each feeding episode can light up a galaxy's core as a quasar. What we see today may be the end result of countless chapters of growth that played out over cosmic time. Black holes can grow by pulling in gas, dust, and even stars. Growth is not usually a single dramatic gulp. It is often a steady process, like a gravitational tide drawing material inward bit by bit. Gas clouds can drift too close and begin to spiral toward the center, heating as they fall and radiating energy away. Dust rides along with that gas, and it can hide the action from ordinary telescopes while the region blazes in other wavelengths. Sometimes the meal is far more dramatic. A star can wander into a region where gravity changes sharply over short distances, and the star is stretched and torn apart. Part of that shredded material escapes, but part can settle into a hot, swirling flow that feeds the black hole for months or years. Over long timescales, this steady diet can turn a modest black hole into a much larger one. Matter falling toward a black hole heats up and glows brightly. Gravity does not just pull material inward. It also converts motion into heat as gas collides, compresses, and churns on the way down. The closer the gas gets, the faster it moves, and the more violently it rubs against itself. That friction and compression can raise temperatures high enough to produce intense radiation, often in ultraviolet and X-rays. In some systems, this light flickers and flares as the flow becomes unstable, like weather in a stormy atmosphere. In others, the brightness can surge when a new supply of gas arrives. The remarkable point is that the black hole itself stays dark, yet the region around it can become one of the brightest places in the universe. By studying that glow, astronomers learn how matter behaves under extreme gravity, and they can infer properties of the hidden object doing the pulling. This glowing matter forms a spinning structure called an accretion disk. When gas approaches a black hole, it rarely falls straight in. It usually arrives with some sideways motion, which means it carries angular momentum. Instead of plunging immediately, the gas settles into a flattened rotating disk, with inner regions orbiting faster than outer regions. That shear creates friction and turbulence, which lets the gas lose energy and drift inward in a slow spiral. The disk can be thin and bright in some systems, or thick and chaotic in others, depending on how much material is supplied. Near the inner edge, gravity is so strong that a small change in distance makes a big change in orbital speed. That is where temperatures soar and radiation pours out. The disk becomes a kind of glowing map of gravity, and its light carries information about orbits, magnetic fields, and the geometry of spacetime close to the event horizon. Accretion disks can shine brighter than entire galaxies. This sounds impossible until you remember what a galaxy is. A galaxy is hundreds of billions of stars. Yet an actively feeding supermassive black hole can release enormous energy from a region that is tiny compared with a galaxy's full size. The reason is efficiency. When matter falls deep into a gravitational well, a surprising fraction of its energy can be converted into radiation before it disappears. In some cases, that energy output can dominate the light from every star in the host galaxy combined. Seen from far away, the bright core can look like a star, even though it is powered by a black hole millions or billions of times heavier than the Sun. These brilliant objects are called quasars. They can be visible across the observable universe, which means they let us study the early cosmos by using black holes as beacons. Some black holes launch powerful jets of particles into space. Not all of the infilling material ends up swallowed. In some systems, a portion is redirected into narrow beams that shoot outward from the poles. These jets are made of charged particles moving at extreme speeds, and they are guided by intense magnetic fields around the black hole and its disk. Jets can shine in radio waves, visible light, and X-rays, depending on their energy and environment. They can also vary in brightness, as if the engine turns up and down. What makes this especially gripping is that the jets can carry more energy than the black hole receives from the matter it actually consumes. The system acts like a natural particle accelerator, powered by gravity and rotation. By studying jets, scientists probe how magnetic fields behave in the most extreme conditions we know, and how energy can be focused into astonishingly narrow streams. These jets can extend far beyond their host galaxies. A galaxy is already huge, so the scale here is hard to hold in your mind. Some jets travel so far that they reach well into the space between galaxies, forming enormous radio-glowing lobes where they slam into thinner gas. Along the way, they can punch through surrounding material and carve out long channels in the galaxy's halo. This matters because galaxies do not evolve in isolation. They live in a larger environment filled with gas that can cool, collapse, and form new stars. A powerful jet can heat that gas, stir it, or push it outward, changing the future of star formation across an entire region. In that sense, a black hole can influence places that are vastly larger than the black hole itself. The central engine is small, but the consequences can be galaxy-sized or larger. That contrast is one reason jets remain one of the most dramatic signs of black hole activity. Jets travel close to the speed of light. When something moves that fast, the universe starts playing tricks on your expectations. Motion near light speed changes how brightness looks, how time intervals appear, and how signals arrive. A jet aimed roughly toward Earth can seem brighter than it would otherwise be, because its radiation is boosted by its motion. The jet can also appear to change position rapidly, creating the illusion of faster-than-light motion across the sky. Nothing is actually outrunning light. It is a viewing effect caused by geometry and timing. The particles inside the jet carry enormous energy, and when they interact with magnetic fields, they can produce intense radiation across many wavelengths. These speeds also mean jets can remain narrow over long distances, because the flow has so much momentum. When you watch a jet, you are watching relativity not as an abstract idea, but as an observable behavior written across the sky. Magnetic fields help shape and power these jets. Gravity supplies the raw energy by pulling matter inward, but magnetic fields help decide where that energy goes. In the swirling flow near a black hole, magnetic field lines can be stretched, twisted, and amplified, like elastic threads caught in a whirlpool. Those fields can channel charged particles into tight streams and keep the jet collimated, instead of spreading out. They can also tap into the rotation of the disk, and in some models, even the rotation of the black hole itself, transferring rotational energy outward. This is why jets are so closely studied in radio astronomy, because magnetic processes leave strong signatures in radio light. The details are still debated, but the basic picture is clear. Without magnetism, the outflow would be weaker, messier, and less focused. With it, a system that begins as falling gas can end up as a beam that influences an entire galaxy. Black holes can slowly spin as they consume matter. Spin is a kind of memory of how material arrived. If a black hole feeds from a disk that rotates in a steady direction, the incoming matter carries angular momentum, and that can gradually increase the black hole's rotation. Over long periods, this can lead to very rapid spins. If feeding happens in bursts from different directions, the spin can change in a more complicated way, sometimes speeding up, sometimes being partially cancelled. Mergers can also add or alter spin, depending on how the two black holes were oriented before they combined. Spin matters because it affects the structure of the region near the event horizon. It changes which orbits are stable, how close matter can circle before plunging, and how energy may be extracted into jets. In a sense, the spin is part of the personality of a black hole. It carries the history of how it grew, written into space-time itself. A spinning black hole drags space around with it. This is one of the strangest predictions of general relativity, and it is not just philosophical. Rotation does not merely spin the object. It twists the space-time around it. Near a rapidly rotating black hole, this dragging can become so strong that everything nearby is forced to rotate in the same direction. Even light paths are affected. This creates regions where staying still, in the usual sense, is no longer possible. The effect can influence the inner disk, change how matter falls inward, and alter the direction of jets. It also changes how objects precess. which is a slow turning of orbital orientation over time. When you picture the environment, it helps to imagine space-time as a moving medium rather than a static stage. The black hole's rotation makes that medium swirl. Matter does not only fall through space, it falls through a space that is itself being pulled into motion. This effect is called frame dragging. The frame here means the local reference frame you would use to define directions and rotation. In normal conditions, you can imagine space as fixed while objects move through it. Frame dragging says that near a rotating mass, space-time itself is part of the motion. It has been measured around Earth with precision satellite experiments, but near a black hole, the effect is far stronger and far more consequential. In black hole systems, it can cause the inner regions of an orbiting flow to precess, which can lead to distinctive patterns of variability in the light we observe. It can also influence how matter aligns over time, changing the geometry of the disk. The name is technical, but the idea is vivid. Rotation reaches out into the fabric of reality and tugs on it. The black hole is not just an object with spin. It is a source of spinning spacetime, and that changes the behavior of everything nearby. The faster a black hole spins, the more extreme its effects. Spin changes where the action happens. In a non-rotating case, stable orbits end at a certain distance from the center. With rapid rotation, matter can orbit closer on some paths, which means it can heat up more and radiate more strongly before plunging inward. Rapid spin also strengthens spacetime twisting, which can reshape the inner disk and influence how jets are launched. There is also a limit. A black hole cannot spin arbitrarily fast because at some point the physics of formation and accretion prevents further spin-up. Many observed systems appear to have high spins, and measuring that spin is an active field of research. The methods include studying the shape of X-ray spectra and the way inner disk light is distorted by gravity. What makes the topic gripping is that spin turns a black hole from a static trap into a dynamic engine. The faster it rotates, the more it behaves like a machine made from gravity. Black holes have temperature, despite appearing completely dark. This is one of the great surprises of modern physics. Classical black holes seem like perfect absorbers that never emit anything. Quantum theory changes that picture. It implies that black holes can be associated with a temperature, and that temperature depends on their mass. The larger the black hole, the colder it is. The smaller it is, the hotter it becomes. This ties black holes to thermodynamics, which is the physics of heat, energy, and entropy. It also ties them to the quantum vacuum, the restless background of fields that never truly sit still. The idea that an object defined by darkness and inescapability can still be assigned a temperature is more than a fun detail. It is a clue that gravity and quantum physics are entangled in ways we still do not fully understand. When you hear that a black hole has a temperature, you are hearing the universe hint that our categories are incomplete. They can slowly lose mass through a process called Hawking radiation. The key is that quantum fields near the event horizon behave differently from fields in calm, flat space. In Hawking's picture, the black hole is not perfectly black. Over immense timescales, it can emit radiation and lose a tiny amount of mass as a result. You can think of it as the black hole paying an energy cost associated with the horizon's presence in a quantum world. This is not a stream you could see with a telescope for ordinary black holes. It is incredibly faint. Still, the implication is profound. Black holes are not just endpoints. They can have a long-term evolution that ends, in principle, with evaporation. That turns the black hole story into something with a beginning, a life, and a final chapter, even if that final chapter takes far longer than the current age of the hour. Universe. It also creates new puzzles about what happens to information, which is why the idea remains so central. Hawking radiation is far too weak to detect for large black holes. For stellar and supermassive black holes, the predicted temperature is extremely low, far colder than the cosmic microwave background that fills the universe. That matters because an object colder than its environment tends to absorb more energy than it emits. So, a large black hole would be overwhelmed by incoming background radiation, which hides any tiny quantum glow it might produce. Even in an ideal laboratory, the signal would be unimaginably faint. This is why Hawking radiation remains a theoretical triumph rather than an observational one. Scientists test the underlying ideas in indirect ways, including experiments with analog systems that mimic horizon-like behavior in fluids, optical setups. Those are not black holes, but they can reproduce some of the relevant mathematics. The practical challenge is part of what keeps the topic compelling. A prediction that reshaped physics is still beyond direct measurement for the black holes we actually observe. The universe has handed us a clue, but it has not yet given us the easy way to check it. Small black holes would evaporate much faster than large ones. The mass dependence flips intuition. A smaller black hole has a higher temperature in the Hawking picture, which means it would radiate more strongly, lose mass more quickly, and speed up its own evaporation as it shrinks. It is a runaway process. As it gets smaller, it gets hotter, and as it gets hotter, it evaporates faster. In the final stages, the theory suggests the radiation could become intense, perhaps ending in a brief burst. This is one reason scientists are interested in the possibility of tiny black holes from the early universe. If such objects ever existed with the right masses, their final moments might leave detectable signatures, such as flashes of high-energy particles or gamma rays. The details depend on unknown physics, including what happens at the smallest scales where quantum gravity takes over. Still, the overall lesson is striking. Big black holes change slowly, almost like geological features of spacetime. Small ones would be fleeting and violent, more like sparks. No evaporating black hole has ever been observed. That absence is meaningful because it limits how many small black holes can exist and what their masses could be. Astronomers look for signals that could match an evaporation event, such as unusual bursts of high-energy radiation, but none has been confirmed as a black senna. Oh, finale! There are also broader searches for the effects small black holes might have had over cosmic history, including how they would contribute to background radiation, or alter the early universe's chemistry. The lack of a detection does not disprove the idea. It tells us that if these objects exist, they are either rare or they occupy mass ranges that make them hard to spot. In science, non-detections can be as informative as detections because they draw boundaries around what is possible. Here, the boundary is a tantalizing one. A famous prediction says black holes can fade away. The universe has not yet shown us a clear example, so the mystery stays open and sharp. Black holes are among the simplest objects allowed by physics. This is the contrast that makes them so compelling. The environments around black holes are messy, bright, turbulent, and chaotic. Yet the black holes themselves are remarkably spare in how they are described. They do not carry features like mountains, atmospheres, or chemical layers. In the simplest view, once a black hole settles down, only a small set of properties matters for the external universe. That simplicity is not a weakness. It makes black holes powerful test objects because the theory gives precise predictions with fewer moving parts. It also makes the information puzzle feel sharper. If something complex falls in, the outside description looks simple. Understanding how those statements can both be true is one of the reasons black holes sit at the center of modern theoretical physics. They are like a clean mathematical object embedded in a very noisy universe. That combination is rare and scientifically priceless. A black hole is fully described by mass, spin, and electric charge. This idea is often called the no-hair picture, and it is one of the cleanest statements in modern physics. No matter what formed the black hole, and no matter what fell in later, the outside world can only measure a small set of traits once the system settles down. Mass tells you how strong the gravity is. Spin tells you how space-time is twisted by rotation. Charge tells you how it would interact electrically, at least in principle. Everything else, like the original star's chemistry or a swallowed planet's shape, disappears from the outside description. That simplicity is not just a curiosity. It led scientists test gravity with unusual precision, because the predictions are sharp. If the real universe ever shows a settled black hole with extra measurable features, that would be a major clue that our theory is missing something fundamental. Most real black holes have almost no electric charge. Charge is easy to build in a laboratory, but space is not a quiet laboratory. The regions around black holes are filled with plasma, and plasma carries both positive and negative charges that move freely. If a black hole gained even a modest net charge, it would immediately start attracting opposite charges from its surroundings. Those charges would fall in and neutralize it. On top of that, any strong charge would repel charges of the same sign, which makes it hard to keep piling charge on in the first place. The result is that astrophysical black holes end up close to electrically neutral most of the time. That is useful, because it means their behavior is dominated by gravity and rotation, rather than electric effects. It also explains why the most dramatic signals we see, like hot disks and jets, are not powered by the black hole acting like a giant battery. They are powered by motion, magnetism, and gravity working together in extreme conditions. Black holes can merge with other black holes. For a long time, this sounded like a rare event, because black holes are small targets in a huge galaxy. Nature found ways to make it happen anyway. Two massive stars can form as a pair, live as a pair, and die as a pair. If both collapse into black holes, the system can remain bound. Star clusters offer another route. In dense clusters, close gravitational encounters can swap partners and harden pairs, which means the black holes end up in tighter and tighter orbits. Once a pair is close enough, gravity itself starts draining orbital energy through gravitational waves. The orbit shrinks, the black holes circle faster, and the finale becomes inevitable. The last moments are unimaginably fast. Two invisible objects race around each other and then become one, leaving behind a single remnant whose mass and spin carry the history of that violent union. Merging black holes release energy as gravitational waves. The energy does not leave as light because there may be little or no matter nearby. Instead, it leaves as ripples in space-time itself. As the two black holes spiral inward, the waves grow stronger and faster, like a rising chirp. In the final moments, the system releases an enormous amount of energy in a very short time, yet the signal can still arrive at Earth as a change in distance smaller than the width of an ATTOM. That contrast is part of the wonder. The event is among the most powerful in the universe, but by the time it reaches us, it is a whisper. After the merger, the newly formed black hole rings, like a struck bell made of space-time. The wave pattern contains the imprint of mass and spin, which is why these detections are not just dramatic. They are measurements that let us check our deepest ideas about gravity in its most extreme form. Gravitational waves stretch and squeeze space as they pass. This is not a metaphor, it is what the waves do. As a wave moves through an area, it changes the geometry of distances in a rhythmic pattern. One direction becomes slightly longer while a perpendicular direction becomes slightly shorter. Then the pattern flips. Everything in that region is affected together, including rulers, mirrors, and the space between them. That is why the effect is so hard to detect. You cannot shield yourself from it, and you cannot compare against a perfectly fixed object because the wave changes the whole region. The only way is to measure relative changes with extraordinary precision. Interferometers do this by splitting laser light, sending it down long arms, and comparing how the light recombines. A passing wave shifts the timing just enough to produce a detectable pattern. When you hear that a black hole merger was observed, this is what it means. Humanity measured space-time itself flexing, then traced that flex back to a distant collision. Scientists first detected gravitational waves in 2015. For decades, gravitational waves were a beautiful prediction and a stubborn experimental challenge. Then a signal arrived that was too clean to ignore. In September of 2015, the LIGO detectors recorded a brief pattern that matched the expected shape of two black holes spiraling together and merging. The announcement came months later after careful checks, because a discovery that large has to survive every possible doubt. This was not a vague hint. The signal showed a clear rise in frequency and strength, followed by a sharp end, exactly like the last moments of a merger and the settling of the remnant. It also came from far beyond our galaxy, which means the waves traveled for an immense span of time before reaching Earth. The detection opened a new kind of astronomy. Telescopes see light. These instruments listen to the motion of mass, even when there is no light at all, and that changes what parts of the universe are available to us. That detection confirmed a major prediction of general relativity. General relativity does more than explain why planets orbit and why clocks tick differently in gravity. It predicts that accelerating masses can send out ripples in space-time. For years, the theory passed every test in the solar system, but black hole mergers probe a far more extreme regime. The first gravitational wave signal matched the relativity prediction not only in broad shape, but in detailed timing. The in-spiral phase followed the expected pattern. The merger produced a peak consistent with strong field gravity. The ring-down matched the idea that a new black hole should settle into a stable state with a specific vibration signature. This matters because it tests gravity where alternative theories might diverge. It also turns black holes into laboratories. You cannot build a black hole merger in a lab, but the universe builds them for you and sends the data to Earth through space-time itself. That is a remarkable scientific gift, and it places general relativity under the brightest spotlight available. Gravitational wave signals reveal the masses of merging black holes. A waveform is not just a detection, it is a fingerprint. The rate at which the chirp climbs depends on the masses. Heavier pairs spiral together differently from lighter pairs, and the final merger peak shifts too. By matching observed signals to a library of predicted waveforms, scientists can estimate the masses of the two original black holes and the mass of the final coup. Remnant. The same signal also carries hints about spin, because spin changes the dynamics of the orbit and the moment of merger. What makes this so powerful is that it works even when the system is completely dark. There may be no hot gas and no light to measure, yet the masses can still be inferred from the space-time pattern alone. This is one reason gravitational wave astronomy expanded so quickly. It can weigh objects that are otherwise invisible. In a sense, it turns mass into sound, and it lets us do astronomy with the structure of time itself as the messenger. Some detected black holes were heavier than expected. Before gravitational wave detections, most known stellar mass black holes came from X-ray binaries, and they tended to cluster in a narrower mass range. Then the merger signals arrived, and some components looked surprisingly heavy. That forced scientists to revisit ideas about how massive stars live and die. A key issue is mass loss. Stars can shed enormous amounts of material through stellar winds, and the strength of those winds depends on factors like chemical composition. If a star loses less mass before collapse, it can leave a heavier remnant. Another issue is pair instability, a process that can disrupt very massive stars and prevent certain black hole masses from forming in the simplest models. When detectors began finding objects near these boundaries, it raised new questions. Were these black holes formed through unusual stellar evolution, through repeated mergers in clusters, or through something else entirely? The surprise was not just a bigger number. It was a clue that nature is using more than one pathway to build black holes. These discoveries changed ideas about how black holes form. Once you have a new way to observe the universe, you also get new ways to be wrong, which is healthy for science. Gravitational wave catalogs started to show patterns, including mass ranges, spin distributions, and hints about how often mergers happen. Those patterns feed back into models of stellar evolution and star formation. For example, if many merging black holes come from low metallicity environments, that points to specific eras of cosmic history and specific types of galaxies. If many mergers come from dense clusters, that points to a different story, where repeated interactions and partner swapping are important. Spin measurements can also hint at origin. Aligned spins suggest long-lived binary evolution. Random spin orientations suggest dynamical pairing. None of these clues is perfect on its own, but together they reshaped the field. Black holes stopped being rare curiosities and became a population that can be studied statistically. That shift is huge. It turns questions like, can this happen, into questions, like how often does it happen, and why that way? Black holes can also merge with neutron stars. This pairing is a collision between two extreme kinds of remnants. A neutron star is matter-packed so tightly that atoms are crushed and the star becomes a city-sized sphere. When a black hole is in the mix, the outcome depends on mass and spin, and also on how compact the neutron star is. In some cases, the black hole simply swallows the neutron star with little debris left outside. In other cases, the neutron star can be torn apart before the final plunge, which spreads material into space. That difference matters because debris can power light signals that accompany the gravitational waves. These mergers also help scientists study the neutron star equation of state, which is the relationship between pressure and density inside that ultra-dense matter. The waveform can carry information about tidal effects, and the presence or absence of bright aftermath can narrow down what happened. It is like watching gravity and nuclear matter collide in the same story, and both leave clues. These mergers can produce bursts of light and heavy elements. When a neutron star is disrupted, some of its material can be flung outward at high speed. That ejected matter is rich in neutrons, and it can rapidly build heavy atomic nuclei through the AR process. The fresh elements then heap the debris as radioactive isotopes decay, producing a glow called a kilonova. The light changes color over days as different elements dominate and as the material expands and cools. This is one of the most satisfying kinds of cosmic evidence because it connects a violent astronomical event to the chemical story of the periodic table. It also gives astronomers two messengers at once. Gravitational waves provide the timing and the masses. Light provides the environment and the material outcome. When both are seen, the event becomes a full narrative rather than a single signal. It also helps map where heavy elements come from in the universe. That is a question with direct relevance to our own planet, because the atoms in jewelry and electronics have an astrophysical origin story. Elements like gold may form during such collisions. Gold is a useful example because it is familiar and because it is rare. In the R process, atomic nuclei capture neutrons quickly, building heavier and heavier elements before they can decay. The ejected debris from neutron-rich mergers provides a natural environment for that rapid buildup. Over time, unstable nuclei decay into more stable ones, and the result can include elements in the gold family and beyond. This does not mean every piece of gold on Earth came from one event, and it does not mean black hole and neutron star mergers are the only source. It does mean that at least some of the gold in the cosmos likely began as freshly made nuclei in expanding merger debris long before the Sun formed. The next time you see gold, it is worth remembering that it may have started as hot, dense matter launched into space by a collision so intense that it shook spacetime. That is an origin story with real physics behind it, and it ties everyday objects to the most extreme events we can observe. A star that wanders too close can be torn apart. This is where the word spaghettification comes from, and it is as dramatic as it sounds. The side of the star closer to the black hole feels a stronger pull than the far side. When that difference becomes large enough, the star is stretched into a long stream. The star's own gravity cannot hold it together, and the star is shredded into a mixture of hot gas and debris. Some of that material is flung outward, and some falls inward and forms a temporary accretion flow. The system can flare to extraordinary brightness for weeks or months, even though the black hole itself remains dark. These events are also time-dependent, which makes them exciting to observe. You can catch a galaxy that looked ordinary last year, and then suddenly its center is blazing because a star met the wrong orbit. It is a reminder that galactic cores are not static. They are active gravitational environments where a single close pass can destroy a star and light up a galaxy's heart. This event is called a tidal disruption event. The name is clinical, but the reality is violent and scientifically rich. Tidal forces are the same basic idea that raises ocean tides on Earth, except here the gradient is so steep that it can rip a star apart. After disruption, the debris follows a range of orbits. Some escapes, but a significant fraction can return toward the black hole over time. That fallback rate often declines in a distinctive way, which gives astronomers a kind of clock to study. The returning gas can form a disk, produce strong ultraviolet and X-ray emission, and sometimes launch outflows. Observers look for sudden brightening in a galaxy's nucleus and then track how the spectrum and brightness evolve. Because the event begins abruptly, it is like a natural experiment with a clear start time. It lets scientists study how an accretion flow turns on, how jets might form, and how a black hole reacts when it is suddenly fed. It also provides a rare chance to probe black holes in galaxies that were otherwise quiet, because disruption can reveal a hidden central mass. Tidal disruption events can be seen across vast distances. They are bright enough that modern sky surveys can find them by scanning large areas repeatedly and flagging sudden changes. This is time-domain astronomy, where the key information is not just what is in the sky, but what is changing. When a candidate flare is found, follow-up telescopes can measure its spectrum, its color evolution, and its X-ray behavior. The combination helps distinguish disruption events from supernova and other transients. Some are found in optical light. Others show up strongly in ultraviolet or X-rays. A few show evidence of jets aimed toward us, which makes them even brighter through relativistic boosting. Because these events can be detected far away, they help scientists build a census of black holes in many galaxies, including ones that do not host luminous, active nuclei most of the time. They also let us watch the process of stellar destruction unfold, rather than inferring it from a static snapshot. That is powerful, because it turns a theoretical picture into a sequence you can actually observe and compare across many cases. Black holes can remain quiet for long periods. A black hole does not need to be actively feeding to exist, and many spend most of their lives in a low-activity state. The key factor is supply. If there is little nearby gas, or if gas has too much angular momentum to fall inward efficiently, the black hole may have very little to accrete. Even in galactic centers, gas can be locked up in stars or kept hot and diffuse, which reduces feeding. The result is a central black hole that is gravitationally important but electromagnetically faint. This quiet phase matters because it is likely the common state rather than the exception. It also affects how we interpret the universe. If you only looked for bright, active black holes, you would miss most of them and get a distorted picture of black hole demographics. Quiet black holes are like dormant volcanoes. They can still shape the landscape through gravity, and they can still wake up if conditions change. But for long stretches, they may barely announce themselves in light. Quiet black holes are difficult to find. When a black hole is not surrounded by bright, hot gas, it does not advertise its presence. Astronomers then have to rely on subtler techniques. One method is to track the motion of a visible companion in a binary system, looking for an unseen mass that is too heavy to be a normal star. Another is gravitational microlensing, where a passing compact object briefly magnifies the light of a background star and can also shift the star's apparent position. Astrometric surveys can search for tiny wobbles in a star's motion that suggest an invisible partner. Each approach has challenges. Microlensing events are rare and unpredictable. Orbital studies require time and precision. Crowded regions make measurements harder. Yet progress is steady and the reward is significant. Finding quiet black holes helps map how common they are, how massive they tend to be, and how they are distributed through the galaxy. It also checks our models of stellar death, because every quiet black hole is evidence of a past collapse that may not have produced a dramatic, visible supernova. Some black holes may drift alone through galaxies. Not every black hole stays neatly in a binary or anchored in a galactic nucleus. When massive stars explode, the explosion can be asymmetric, and that can kick the remnant. If the kick is strong enough, a newly formed black hole can be launched onto a wandering path through the galaxy. Over time, it may pass through interstellar clouds, or it may move through relatively empty regions with little to accrete. That makes it almost invisible. Still, its gravity is real. In principle, such a drifter could reveal itself by microlensing a background star, or by accreting a small amount of gas and producing faint X-rays. The idea also changes how we think about the galaxy's population of compact objects. There may be many black holes that are not in bright systems, not in pairs, and not in famous places. They may be moving through the same disk of stars that contains our solar system, separated by vast distances, and detectable only through careful surveys that look for the smallest gravitational signatures. These are sometimes called rogue black holes. The word rogue is not a scientific classification, but it captures the basic idea. A black hole that is not obviously tied to a star system or a galactic center is hard to spot and easy to underestimate. Searches often focus on microlensing events that last for weeks or months, because heavier lenses tend to produce longer signals. If a lensing event also shows a measurable shift in the background star's apparent position, scientists can better infer the lens's mass and decide whether it could be a tessile POOD. Black hole. Space missions that map stellar positions precisely, like Gaia, make this kind of hunt more realistic. A confirmed rogue black hole would be a striking object. It would be nearby by cosmic standards, massive, dark, and moving, with no bright disk to warn you that it exists. It would also add an important piece to the census of black holes in the Milky Way and help answer a simple question with big consequences. How many invisible heavy objects share our galaxy with us? A black hole does not actively pull objects toward it. Gravity is not a hunting force that reaches out and grabs. It is the shape of space-time, and objects follow that shape unless something changes their motion. Far from a black hole, a spacecraft can orbit just as it would around any object with the same mass. If it has enough sideways speed, it keeps missing the center and continues circling. To fall in, it must lose orbital energy or lose the sideways motion that keeps it in a stable path. That is why black holes can exist in busy regions without immediately swallowing everything nearby. Stars can orbit a central black hole for millions of years. Gas clouds can pass by and continue on their way. The danger rises when something wanders close enough that gravity changes sharply across short distances, or when friction and collisions remove the motion that was keeping it safe. Objects must lose energy to fall inward. Falling into a black hole usually looks less like a straight drop and more like a long spiral. Something in orbit has energy and angular momentum, which act like a kind of built-in resistance to plunging. To move inward, that energy must be carried away. For gas, the main mechanism is friction and turbulence. Colliding streams heat up and radiate light, and that radiation leaves the system, taking energy with it. Magnetic interactions can also move angular momentum outward, allowing inner material to drift down. For stars in crowded environments, repeated gravitational encounters can shuffle energy between objects, pushing some inward while flinging others outward. In very tight black hole pairs, gravitational waves do the same job on a grand scale, stealing orbital energy until the final plunge becomes unavoidable. The key idea is simple and powerful. In space, falling often requires a way to get rid of energy, not a way to gain it. Stable orbits exist outside a black hole's event horizon. A black hole does not erase the usual rules of orbital motion the moment you approach it. There are still paths where an object can circle for a long time, and those paths can be very predictable. This is why disks can form and persist, and why stars can trace repeated loops around an unseen center. The difference is that close to the black hole, the landscape of possible orbits changes. Some orbits become unstable, which means a tiny disturbance can turn a safe loop into an inward plunge. That creates a natural inner edge for many disks, and it helps shape the radiation we observe from hot gas. The spinning black holes, the details depend on whether the orbit goes with the spin or against it. In a sense, a black hole is not just a trap. It is also a gravitational organizer, with a structured map of allowed motions outside its boundary. Inside the event horizon, all paths lead inward. The strangest part is that this is not about being too weak to escape. It is about what forward means. In relativity, the future is a set of possible directions you can move through spacetime. Outside the horizon, some of those future directions point outward, so escape remains possible. At the horizon, the geometry tips so steeply that every future directed path aims toward the center. Even a beam of light that tries to go outward still moves inward in terms of the deeper geometry. This is why the horizon is such a clean boundary. It is not a physical surface that blocks you. It is a boundary in the space of possible futures. That idea can sound abstract, yet it has a clear consequence. Once you cross, turning around is not like turning a vehicle. It is like trying to drive into yesterday. The option simply is not available. The singularity lies at the center of a black hole. In the simplest mathematical descriptions, the collapse does not stop at a dense core. It continues until the curvature of spacetime becomes infinite, and density becomes infinite too. That predicted endpoint is called the singularity. It is not something anyone thinks of as a normal object sitting in space. It is more like a warning sign inside the equations, where the usual concepts of distance and time stop behaving in familiar ways. The singularity is hidden by the event horizon, which is why it does not immediately contradict what we observe. Still, the idea matters, because it tells us where our best theory is being pushed past its safe range. In everyday life, infinities usually mean a model has been taken beyond where it applies. The singularity may be a real feature of nature, or it may be a signal that new physics must appear before the collapse reaches that extreme. Current physics cannot fully describe the singularity. General relativity is brilliant at describing gravity as geometry, but it treats spacetime as smooth and continuous. Quantum physics, on the other hand, tells us that fields have fluctuations and that small scales can behave in surprising ways. A singularity sits exactly where those two frameworks collide. Near such extreme curvature, quantum effects should matter. Yet we do not have a complete theory that unifies quantum rules with gravitational geometry. That is why predictions become unreliable. It is not that the equations give no answer. They give answers that include infinities and contradictions, which is usually the sign that a deeper description is needed. Many researchers expect that whatever replaces the singularity will involve a new picture of spacetime at tiny scales, and possibly a limit to how tightly matter and energy can be compressed. Until that theory is complete, the singularity remains one of the clearest places where physics admits it has reached the edge of its own map. Singularities mark where known theories break down. In physics, a singularity is often less like a destination and more like a red flag. When a calculation produces infinite density or infinite curvature, it usually means the model is being asked to describe conditions it was never built for. That is exactly what happened here. General relativity was designed to describe smooth spacetime and large-scale gravity. It works beautifully for planets, stars, and even the overall evolution of the universe. At a singularity, the smooth picture collapses, and the theory can no longer reliably tell you what happens next. This is not unique to black holes. Similar singularities appear when you run simple models backward toward the very early universe. In both cases, the infinities are telling the same story. Our current tools are incomplete at the most extreme densities. That is why singularities are scientifically valuable. They are not just weird results. They are signposts that point directly toward the missing pieces of our understanding. Quantum gravity may change how singularities behave. Many approaches try to build a theory where spacetime itself has quantum properties. In some ideas, space is made of tiny units, so there is a smallest meaningful scale. In others, geometry emerges from deeper ingredients, like information and fields that behave differently at high energy. If space-time has a built-in graininess or a new set of quantum rules, then the runaway collapse predicted by classical relativity might be halted or redirected. Instead of an infinite point, the core might reach an extreme but finite density. Some models suggest a bounce, where collapse transitions into expansion under quantum pressure-like effects. Others suggest that what we call the singularity is replaced by a region where familiar notions of time and distance become fuzzy, but not infinite. These ideas are still being tested, mostly through mathematics and consistency checks, because direct experiments are hard. Still, black holes remain one of the best places to search for quantum gravity's fingerprints, because they push nature into the strongest curvature we can observe. Some theories suggest singularities may not truly exist. There are proposals where a collapsing object never forms the classical interior predicted by simple equations. Instead, exotic states of matter or new gravitational behavior could create an ultra-compact object that looks almost like a black hole from outside. Some ideas involve a shell or a vacuum-like interior that resists complete collapse. Others propose that quantum effects could create a long-lived remnant, so the endpoint is compact and extreme, but not mathematically infinite. These alternatives are difficult to test because, from far away, many would mimic a true black hole very closely. The differences might appear in subtle ways, such as how the object rings after a merger, or how matter behaves at the innermost edge of an accretion flow. That is why this question stays alive. The singularity is hidden, so nature gives us only indirect clues. Yet the stakes are enormous. If singularities do not exist, then the universe avoids true infinities, and that would reshape how we think about what reality allows at its most extreme: limits. These questions remain open and actively studied. Black holes sit at the intersection of observation and theory in a rare way. Telescopes can track stars orbiting invisible masses, radio arrays can map the glow of gas near an event horizon, and gravitational wave detectors can record the aftershocks of mergers. At the same time, theorists are wrestling with deep questions about information, quantum behavior, and what spacetime is made of. Progress often comes from connecting these worlds. A new observation can eliminate a class of models. A new mathematical insight can suggest what signature to look for in the sky. Even the absence of a signal can be revealing, because it constrains how extreme certain effects can be. This is why black hole research moves so quickly. It is not a single problem with one answer. It is a network of mysteries that reinforce each other, from the largest scales of galaxies to the smallest scales where quantum gravity might live. Each new dataset is a new chance to learn what the universe does when it is pushed to the edge. Wormholes are theoretical tunnels through spacetime. A wormhole is a proposed shortcut that connects two separate regions of spacetime through a kind of bridge. In equations, it can look like a throat that you could, in principle, pass through, emerging somewhere else without traveling the long way across ordinary space. The idea is captivating because it turns geometry into a route. Distance becomes negotiable. Yet the same equations that allow wormholes also raise difficult questions about stability. Many wormhole solutions appear to pinch off before anything could cross. Others require unusual energy conditions that do not resemble ordinary matter. Even so, wormholes remain useful because they test our understanding of relativity and the structure of space-time. They also appear in science fiction for good reason. If anything like a traversable wormhole existed, it would change what travel means, and it would force a new conversation about causality and time. For now, wormholes remain a mathematical possibility, not an observed feature of the universe. Some wormhole solutions are mathematically related to black holes. One of the earliest connections appears in the geometry of a non-rotating black hole. If you extend the solution in a certain way, the mathematics can describe two regions of spacetime connected by a bridge. This is sometimes called an Einstein-Rosen bridge. The key detail is that in the simplest version, it is not a usable tunnel. It closes too quickly for anything to pass through. Still, The relationship matters because it shows how black holes and wormholes can be part of the same family of space-time structures in relativity. In modern theoretical physics, there are also ideas that link entanglement and geometry, suggesting deep connections between quantum links and wormhole-like descriptions. These are advanced concepts, but the headline is clear. Black holes are not just astrophysical objects. They are also gateways into understanding what space-time can do in the language of mathematics. Wormhole links keep appearing because black holes are where geometry becomes most flexible and most strange. No wormhole has ever been observed. If a traversable wormhole existed nearby, it might produce distinctive gravitational lensing patterns that differ from ordinary massive objects. It might create unusual multiple images of background stars, or lensing that changes in a way that does not match a simple mass distribution. People have proposed searches for these signatures, and some surveys could, in principle, catch hints, but nothing has been confirmed. Part of the challenge is that many exotic objects can mimic each other from a distance. A wormhole, a black hole, and certain dense star clusters can all bend light in dramatic ways, and the differences can be subtle. There is also the problem of rarity. Even if wormholes are allowed by physics, the universe may not produce them often, or they may require conditions that never occur naturally. So at present, wormholes remain a compelling hypothesis rather than a part of established astronomy. That is not a failure. It is an invitation to sharpen predictions and to keep looking. Some of the best discoveries began as ideas that seemed too strange to be real. Many wormholes would collapse too quickly to travel through. The main difficulty is stability. In many models, the throat of a wormhole is like a tunnel made of space-time curvature, and ordinary matter does not hold it open. Gravity tends to make the tunnel pinch shut. To keep it open, some solutions require forms of energy that behave in unusual ways, often described as negative energy density. In everyday experience, energy density is positive. Negative energy is not a substance you can scoop up, but quantum theory does allow certain constrained effects where energy can be lower than the surrounding vacuum star, for short times and in small regions. The famous Casimir effect is one example of vacuum behavior that hints at this strange territory. Even if such effects exist, scaling them up to hold a macroscopic wormhole open is a huge leap. This is why many traversable wormhole ideas remain speculative. They are not ruled out by math alone, but they seem to demand ingredients that nature may not provide in large, stable amounts. White holes are theoretical opposites of black holes. If you reverse the direction of time in certain black hole solutions, the math can produce an object that nothing can enter, while things can leave. That is the basic white hole concept. It is fascinating because it turns the usual story inside out. Instead of an event horizon that seals things in, you would have a horizon that prevents entry. The object would behave like a one-way outlet in space-time. In theory, it could eject matter and light, and nothing could cross inward to stop it. This raises immediate questions about realism. In our universe, we see plenty of things falling inward under gravity, and we see horizons forming from collapse. We do not see objects that spontaneously spew matter in a way that cannot be traced to an explosion or a star. Still, white holes remain useful as thought tools. They help clarify how time symmetry appears in equations, and how the real universe chooses one direction of time through thermodynamics and entropy. A white hole would expel matter instead of absorbing it. The defining behavior would be a kind of cosmic refusal. Any attempt to send something in would fail, because the horizon structure would not allow inward crossing. Yet outward crossing would be allowed, so the object could, in principle, eject particles and radiation into the surrounding space. The immediate puzzle is where that outgoing material comes from and why it would be released in the first place. In realistic astrophysics, we expect causal histories. We expect a source that can be followed backward to earlier states. A white hole challenges that expectation because it looks like matter emerging without an ordinary precursor that you can observe. Some researchers have explored whether white hole-like behavior could appear in limited or transitional ways, such as in exotic models where collapse is replaced by a bounce. These remain speculative. What is certain is that the concept forces clear thinking about horizons and time. Black holes are natural outcomes of collapse. White holes are the time-reversed story, and the universe has not shown us clear evidence that it runs that story forward. No confirmed white holes have ever been found. Astronomers do see sudden bursts and energetic events, but they have conventional explanations. Supernova mark stellar death. Gamma-ray bursts can come from collapsing stars or compact object mergers. Outbursts from galactic centers can come from changes in accretion. None of these require a white hole. For a white hole claimed to be convincing, it would need a signature that cannot be easily produced by known processes, and it would need consistent follow-up evidence. That is a high bar, and so far it has not been met. This does not mean the idea is useless. White holes are part of the broader effort to understand what the equations allow and how the real universe selects certain solutions over others. Sometimes the value of a concept is in the questions it clarifies. Why do we see horizons form through collapse, but not horizons that force matter outward? What role does entropy play? What role does cosmic history play? The absence of evidence keeps the idea in the realm of speculation, but it also sharpens the contrast between mathematical possibility and physical reality. Black holes appear naturally in Einstein's equations. When Einstein wrote down general relativity, he created a new language for gravity. Almost immediately, researchers began exploring what the equations permit. One of the first exact solutions described a spacetime outside a simple spherical mass. Taken seriously, that solution implied a boundary beyond which escape becomes impossible. At the time, this was not framed as a real object in the sky. It was a feature of the mathematics. Yet the math was stubborn. It kept pointing to horizons as a natural outcome of strong enough compression. Later solutions extended the picture to include rotation, which is essential because real astrophysical objects spin. The remarkable thing is that black holes were not added as an extra idea. They fell out of the equations once gravity was described as curvature. In that sense, black holes are not exotic exceptions to relativity. They are among its most direct and unavoidable predictions, waiting for the universe to show whether it takes advantage of that possibility. Einstein himself doubted they existed in reality. This was not because the equations were wrong. It was because the physical interpretation was unsettling, and the idea of a true horizon felt too extreme. Early discussions often treated the horizon as a mathematical artifact rather than a real boundary. There was also the question of formation. Could a real star collapse far enough to produce such a region, or would some other effect intervene? Even within relativity, it took time for the community to clarify which features were coordinate issues and which were physical. As the decades passed, the picture sharpened. Relativity did not merely allow black holes. It suggested collapse could produce them under realistic conditions. Einstein's caution is worth remembering because it shows how science progresses. Even a revolutionary theory can produce predictions that feel too strange to accept at first. Doubt is not failure. Doubt is the pressure that forces ideas to earn their place through clearer mathematics and, eventually, evidence from the sky. Evidence slowly accumulated over the 20th century. The case did not turn on a single dramatic observation. It built step by step. Astronomers discovered extremely bright galactic cores that suggested compact power sources. X-ray astronomy revealed systems where invisible objects pulled gas from companions and heated it to extreme temperatures. Improved telescopes made it possible to track stellar motions near galactic centers, revealing enormous masses packed into tiny regions. Theoretical work also matured, showing how collapse could proceed and how accretion could generate the observed radiation. By the late 20th century, black holes were no longer just mathematical curiosities. They were the best explanation for multiple classes of phenomena across different wavelengths. The shift was cultural as well as scientific. The term black hole entered public language, and the object moved from fringe speculation into the core of astrophysics. What began as an uncomfortable implication of equations became a central tool for understanding galaxies, high-energy light, and the behavior of matter under Pingler. Extreme gravity. Early black hole candidates came from X-ray observations. When astronomers first opened the X-ray sky, it looked nothing like the calm, familiar night. Instead of steady starlight, there were fierce, flickering sources that seemed to switch on and off. Many of them sat inside our own galaxy, and some brightened so strongly that they demanded an explanation beyond ordinary stars. The key clue was variability. These sources could change dramatically on short timescales, which suggested the emitting region was small. That pointed toward compact objects. In several cases, the X-rays appeared alongside evidence for an unseen massive companion. This was the beginning of a new kind of astronomy, where invisible objects were discovered by the violence of their surroundings. Long before we had images or gravitational waves, X-rays gave the first practical trail to follow. They hinted that something dark and massive was feeding nearby. Hot gas near black holes emits strong X-rays. Gas does not glow in X-rays because it is naturally hot. It glows that way because gravity can accelerate it to enormous speeds, then force it to collide and churn. As gas spirals inward, different layers rub and crash into each other. The energy of that motion turns into heat, and the temperatures can rise so high that the radiation shifts into the X-ray part of the spectrum. Near the inner regions, atoms can be stripped of their electrons, leaving a plasma that behaves in ways we do not see on Earth. The X-rays can also carry signatures of motion and gravity. Spectral lines can be broadened by speed and shifted by gravitational effects. Even the flicker of X-ray brightness can reveal how the flow is changing from moment to moment. In a sense, X-rays are a readable language. They tell you that matter is falling deep into a gravitational well and getting punished into brilliance. X-ray binaries helped identify stellar black holes. In these systems, a normal star shares an orbit with a compact, invisible partner. The star can lose gas to its companion, either through a stellar wind or through a stream of material pulled off by gravity. That transferred gas does not usually fall straight in. It forms a hot, rapidly rotating flow that can shine strongly in X-rays. Meanwhile, the visible star's motion can be tracked through shifts in its spectral lines, which reveals how fast it orbits and how heavy its unseen partner must be. When the inferred mass is too large for a neutron star, the simplest answer is a black hole. Some X-ray binaries also show characteristic changes in brightness and spectrum, as if the accretion flow switches between different states. Those state changes became a rich field of study on their own. This is how black holes became tangible. They were not seen directly at first. They were recognized as the missing weight in an orbit, paired with a glowing stream of stolen gas. Supermassive black holes are linked to galaxy formation. Galaxies are not only collections of stars. They are ecosystems of gas, dust, and dark matter, and their centers often host something massive and compact. Evidence now suggests that the growth of a galaxy and the growth of its central black hole are connected. When a galaxy is young and rich in gas, its center can feed a black hole, which can become active and luminous. That activity can also affect the galaxy's future by heating gas or pushing it around. Over time, galaxies merge, and their central black holes can eventually merge too. This creates a long feedback loop between the core and the larger structure. The most striking part is scale. A central black hole is tiny compared with a galaxy, yet it can influence gas across tens of thousands of light years. That makes it hard to treat black holes as mere passengers. They appear to be participants in how galaxies settle, brighten, and mature. Almost every large galaxy hosts a central black hole. This has become one of the most important general statements in modern astronomy. In galaxy after galaxy, careful measurements point to a massive, compact object in the middle. Sometimes the evidence comes from fast-moving stars near the center. Sometimes it comes from gas disks orbiting too quickly to be explained otherwise. Sometimes it comes from the galaxy's history of active phases, when the core was bright enough to outshine its stars. The remarkable thing is how common the pattern seems to be. Our own Milky Way fits it, and so do many galaxies in the nearby universe. This suggests that black holes and galaxies have been growing together for a very long time. It also means that when you look at a large galaxy, you are likely looking at a system with a hidden gravitational anchor at its core. That anchor is not visible in ordinary light, yet it helps organize motion in the central region and influence the galaxy's long-term evolution. The mass of a galaxy correlates with its central black hole. This relationship is one of the cleanest hints that galaxies and their black holes are not independent. When astronomers compare black hole masses with properties of their host galaxies, they find patterns that are too consistent to dismiss as coincidence. In particular, the black hole mass tends to track the mass and the stellar motions of the galaxy's central bulge. It is as if the galaxy's inner structure and the black hole's growth kept pace over cosmic time. The correlation is not perfect, and the scatter is scientifically interesting, but the overall trend is strong enough to guide models. Any theory of galaxy formation now has to explain why a central black hole ends up with roughly the right mass for the galaxy around it. The physics behind the link likely involves gas inflows, star formation, and energy output from active phases. The correlation acts like a constraint. It tells you that whatever shaped galaxies also shaped the growth of their darkest central objects. This suggests galaxies and black holes evolved together. If black holes were only accidental leftovers, you would not expect them to match their hosts so well. Instead, the evidence points toward a shared story. When gas flows into a galaxy's center, it can feed both star formation and black hole growth. When the black hole becomes active, it can influence how much gas remains available for future stars. Galaxy mergers can deliver new gas and also bring in another central black hole, reshaping the core and changing the growth path. Of the long timescales, these processes can produce a kind of co-development. The galaxy supplies fuel and structure. The black hole supplies energy and gravitational influence. This view also reframes what a galaxy is. It is not just a star system with a dark object hidden in the middle. It is a system where the middle can matter enormously. Even when the black hole is quiet, its past active phases may have already altered the galaxy's gas content and star-forming potential. The visible galaxy can carry scars and signatures of an invisible partner that grew alongside it. Black holes influence how galaxies grow and change. The influence is not mystical. It is mechanical and energetic. When a black hole is actively accreting, it can release tremendous power into its surroundings as radiation, winds, and jets. That energy can heat gas in the galaxy's center, making it harder for the gas to cool and form new stars. It can also drive material outward, reducing the supply of star-forming fuel. In galaxy clusters, black hole activity can inflate cavities in hot gas that are visible in X-ray maps, showing that the central engine can reshape the larger environment. This influence helps explain why some massive galaxies stop forming stars and become dominated by older stellar populations. It also helps explain why galaxy growth does not run away indefinitely. Without a regulating mechanism, models often produce galaxies that are too massive and too bright compared with what we observe. Black holes provide a plausible regulator. They are small, but when they feed, they can act like a thermostat for an entire galaxy. They can heat gas and suppress star formation. Star formation requires gas to cool and clump. If the gas stays hot and stirred, it resists collapse. Active black holes can keep gas from cooling in several ways. Intense radiation can ionize gas and raise its temperature. Fast outflows can shock gas and inject turbulence. Jets can deliver energy to surrounding gas over large distances, preventing it from settling into dense clouds. The result can be a galaxy where plenty of gas exists in principle, yet it remains too warm or too disturbed to form many new stars. This helps explain why some galaxies transition from blue, star-forming systems to red, more quiescent systems dominated by older stars. It is a counterintuitive role for a black hole. You might expect a strong gravitational center to draw gas in and promote growth. Instead, the energetic consequences of accretion can do the opposite. The black hole's feeding can limit the galaxy's future star production, changing what the galaxy becomes over billions of years. This process is called feedback. In astronomy, feedback is a way of saying that a process can regulate itself through its consequences. When a black hole accretes more gas, it becomes more energetic. That energy affects the surrounding gas, which can reduce or reshape the future supply of accreting material. In a strong feedback cycle, a burst of black hole activity can heat or expel gas, which slows further accretion and dims the central engine. Later, gas can cool or flow back in, restarting the cycle. Feedback is not only about stopping growth. It can also guide it, setting the pace and the structure of a galaxy's evolution. The term is used widely because it helps connect small-scale physics near the black hole with large-scale outcomes in the host galaxy. It is one of the bridges between black hole astrophysics and galaxy formation theory. Without feedback, many models fail to match the universe we actually see. With feedback, the picture becomes more realistic and more dynamic, with the central engine acting as a regulating influence. The first image of a black hole was released in 2019. For years, black holes were famous for being unseeable. Then astronomers achieved something that sounded impossible. They created an image that revealed the immediate neighborhood of a supermassive black hole. The target was in a galaxy called Messier 87, and the technique required combining radio telescopes across the Earth into a single planet-sized observing system. This is very long baseline interferometry, and it demands exquisite timing, careful calibration, and an enormous amount of data processing. The result was not a photograph in the usual sense. It was a reconstructed view based on radio waves collected from many sites, then combined into a consistent image. Still, the impact was profound. The image gave the public and the scientific community a direct visual handle on an object defined by darkness. It also showed that black hole theory can make testable predictions about what the region near a horizon should look like. The release became a milestone, not only for black holes, but for modern observational astronomy. The image showed a bright ring around a dark center. That ring is not a physical hoop. It is light from hot plasma that has been bent, boosted, and lensed by extreme gravity. The dark center is the shadow, which is the region where light rays are captured rather than reaching the telescope. The bright ring appears because some light paths skim close to the black hole and are redirected toward us. The plasma itself is orbiting at tremendous speeds, and its motion can make one side of the ring appear brighter due to relativistic effects. What made this especially compelling is that the ring shape was not arbitrary. It matched what simulations predicted for a black hole surrounded by glowing material. The image offered a new kind of evidence. It did not rely on tracking stars or measuring X-ray flicker. It showed a structure in the sky that is hard to explain without strong gravity shaping light. The ring and shadow together gave a visual signature that could be compared directly to theory. Back ring comes from light bending around the black hole. In general relativity, gravity is geometry, so light follows curved paths when spacetime is curved. Near a black hole, that curvature is so strong that light can loop partially around before escaping. Some photons can even orbit briefly on precarious paths, and small changes determine whether they escape or fall inward. This creates a concentration of brightness in a ring-like structure. The effect is a form of gravitational lensing, but pushed to an extreme. Instead of producing multiple images of a distant galaxy, it shapes the glow of matter right next to the black hole. This is why the ring is so informative. Its size and shape depend on the black hole's mass and spin, and on how the plasma is distributed. The ring is also a triumph of concept. It shows that black holes can be studied through the behavior of light itself, even though the black hole remains dark. In a way, gravity becomes an optical instrument, and the universe supplies the lens. The image confirmed predictions made decades earlier. Long before the first successful reconstruction, physicists and astronomers had worked out what a black hole should do to surrounding light. They predicted a shadow, a bright ring, and distinctive distortions caused by strong lensing. They also predicted how motion in the accreting plasma could make the image asymmetric. When the image arrived, it lined up with those expectations within the limits of observation. That does not mean every detail was solved, because the plasma is turbulent and the view is complex. It does mean that a core prediction of strong gravity passed a dramatic visual test. This is important because black holes push general relativity into its most extreme regime. Many previous tests were in weaker gravitational fields, like the solar system or binary pulsars. A shadow image is a test closer to the edge, where space-time curvature is intense, and where alternative theories might diverge. Seeing a result that matches the standard predictions strengthens confidence that our understanding of gravity holds up even there. It also turns black holes into objects that can be measured by imaging, not only inferred indirectly. More black hole images have since been captured. After the first target, attention turned to our own galaxy's central black hole, Sagittarius A star. Imaging it is harder in some ways because it is smaller on the sky and the surrounding plasma changes quickly. Still, astronomers produced an image that shows a similar ring-like structure, which added weight to the overall picture. As observing campaigns continue, images are becoming a tool for studying differences between black holes, not just proving they can be imaged at all. Future work aims to map changes over time, to infer how plasma moves and how magnetic fields shape the flow. Imaging also encourages new theoretical predictions that can be checked directly. This is a shift in black hole science. The subject is no longer limited to orbits, flickers, and spectra. It now includes geometry you can literally point to, compare across objects, and refine with better data. Each new image is also a technical achievement because it requires global coordination, precise timing, and careful analysis. The result is a growing gallery of the universe's most extreme neighborhoods. Future telescopes will produce sharper black hole images. Sharpening an image means increasing resolution, and for these targets, that requires longer baselines and better sensitivity. Researchers are exploring additional observing sites, better receivers, and higher observing frequencies that can cut through some of the blurring effects of interstellar bar. Material. There are also proposals that involve placing radio telescopes in space, which would extend the baseline beyond Earth's diameter. With improved resolution, images could reveal more of the structure in the bright ring and potentially show finer features linked to spin and magnetic fields. Another goal is time resolution. If observations can be made quickly enough, images could show changes as the plasma evolves, creating a kind of short movie rather than a single snapshot. That would be extraordinary, because it would let us watch matter moving in the strongest gravity we can observe. Better images would also tighten tests of general relativity, because subtle deviations might show up in shadow shape or brightness patterns. In the coming years, black hole imaging is expected to become less of a once-in-a-generation event and more of a developing observational field, with improving keen, detail, and richer physical interpretation. Some black holes existed very early in cosmic history. Astronomers have found quasars so distant that we see them as they were when the universe was very young. The light has traveled for billions of years, which means these objects were already massive when cosmic time was still in its early chapters. This is a shock at first glance. Building a supermassive black hole takes growth, and growth takes time and fuel. Yet the evidence suggests that some black holes reached enormous masses surprisingly early. This raises a direct question. What were the first seeds? And how did they form so soon after the first stars and galaxies were beginning to appear? The early universe was different. It had denser gas, more frequent mergers, and environments that could funnel material inward efficiently. Still, the existence of such early massive objects forces models to work hard. They are like milestones placed far back on the cosmic road. They tell us that black hole growth was underway almost as soon as galaxies began assembling. These early black holes grew surprisingly fast. To reach supermassive scales quickly, a black hole needs a head start, or an unusually efficient feeding environment, or both. One possibility is that the first seeds were larger than the remnants of ordinary stars. They might have formed from the direct collapse of massive gas clouds, producing a heavier starting point. Another possibility is that early accretion was sustained near the theoretical maximum for long periods, without being choked off by the energy output. Dense, gas-rich early galaxies might have been able to deliver fuel steadily into the center, especially during frequent mergers. There are also scenarios where repeated mergers between smaller black holes contribute to rapid growth. Each route has challenges, and researchers compare them against observations like quasar brightness, host galaxy properties, and the statistics of high redshift AT. Sources. What makes this exciting is that the growth problem is not a niche detail. It connects to the formation of the first galaxies, the behavior of primordial gas, and the emergence of structure in the universe. Fast growth is a clue that the early cosmos was a more efficient engine than we once assumed. Their existence challenges current formation models. If you take a simple model of stellar remnants growing steadily, some of the earliest known quasars look too massive, too soon. That forces either more massive seeds, more efficient feeding, or some combination that changes the timeline. It also forces careful thinking about what limits accretion. Radiation from a bright accretion disk can push back against infilling gas, and that feedback can reduce the growth rate. Yet the early universe seems to have produced objects that overcame those limits in at least some cases. This is why the high redshift quasar population is so valuable. It is not only a set of bright objects, it is a set of constraints. Any successful theory has to explain how massive seeds formed, how gas reached the center, and how growth continued in spite of energetic output. It also has to explain why such objects were rare enough that we do not see them everywhere. In other words, the early black holes are both a success and a problem. They show what nature can do, and they show where our simplest assumptions fail. New theories continue to be proposed and tested. Black hole science advances through a loop between ideas and evidence. When observations show something unexpected, like very massive early quasars or unusual merger masses, theorists propose new formation routes. Then observers look for signatures that could distinguish those routes, such as the environments of quasars, the distribution of spins, or the statistics of gravitational wave events. Some theories focus on direct collapse seeds. Others focus on unusual accretion states that can exceed standard limits for short periods. Others explore the role of dense star clusters and repeated mergers. Future facilities will add pressure and clarity. More sensitive infrared telescopes can find earlier quasars and map their host galaxies. More gravitational wave detectors will find more mergers and fill out population statistics. Better radio imaging can test strong gravity with finer detail. The story is still unfolding, and that is one of its pleasures. Black holes are not a closed chapter of astronomy. They are a living field where new data can reshape the narrative quickly and where the biggest questions are still on the table. Primordial black holes may have formed after the Big Bang. In the early universe, everything was hotter, denser, and changing rapidly. If some regions were slightly denser than average, gravity could have overwhelmed expansion in those spots and collapsed them directly into black holes. That would make these objects older than any star and older than any galaxy. They would also be fossils of the universe's earliest structure, preserved in the form of compact mass. The intriguing part is what they could tell us. Their abundance would depend on how lumpy the early universe was, on tiny scales we cannot easily measure with ordinary telescopes. If they exist, they could also create subtle effects today, like rare gravitational lensing events or a background of high-energy radiation from the smallest grav-1s. They sit at a crossroads between cosmology and black hole physics, and they turn the early universe into a laboratory that might still be leaving clues. These would not come from stars. Stellar black holes are the end of a life story that includes nuclear fusion, layered elements, and often a supernova. A primordial black hole would have none of that ancestry. It would form from raw density, from gravity acting on the universe's earliest material before stars ever lit up. That difference matters because it changes what mass ranges are possible and what environments they inhabit. A star-made black hole is tied to where stars form, which means galaxies, gas clouds, and chemical enrichment. A primordial black hole could exist almost anywhere, including places with little or no star formation. It would also change how we interpret certain observations. If a black hole is found in a region with no plausible stellar origin, or with a mass that is difficult to produce from ordinary stellar collapse, that can raise the question of a non-stellar pathway. This is why the idea remains so compelling. It offers a completely different origin story written into the universe before astronomy even begins. Primordial black holes could range widely in mass. The mass would depend on the scale of the region that collapsed and the moment in cosmic history when it happened. Earlier times correspond to smaller horizon scales, which can lead to smaller black holes. Later times allow larger regions to collapse, which can produce heavier ones. That creates a wide menu of possibilities, from tiny objects to ones that could rival the black holes made by stars. Each mass range comes with different consequences. Very small ones might have evaporated long ago if Hawking radiation applies, leaving potential traces in cosmic backgrounds. Intermediate ones could reveal themselves through gravitational lensing or by disturbing stellar motions. Larger ones could contribute to the population of black holes that later participate in mergers. The breadth is part of the appeal and part of the difficulty. A wide mass range means many possible signals, but it also means no single simple search can settle the question. Instead, scientists test the idea from many angles, ruling out some masses and leaving others still possible. Some could be as small as mountains. It is a strange thought that something with the mass of a mountain could be compressed into an object far smaller than a grain of sand. Size and mass separate completely in this regime. The mountain mass is familiar, but the compactness is not. Such an object would not be dangerous at a distance, because gravity depends on mass and distance, not on how spooky the object is. If one passed near Earth, the most noticeable effect might be gravitational, like a brief lensing of a background star or a tiny disturbance to a spacecraftine. Trajectory if it came extremely close. The real mystery is survival. Small black holes would be hotter in the Hawking picture, which means they would radiate more and might not last to the present day unless their mass is above a certain threshold. That is why the mountain-sized idea sits right on the edge between imagination and testable physics. It is concrete enough to picture and extreme enough to force careful constraints. Others could rival stellar black holes. If primordial black holes exist in this heavier range, they become harder to distinguish from black holes made by collapsing stars. The clues would have to come from context. Are they found in places where massive stars never lived? Do their numbers match what stellar evolution predicts? Do their masses fall into ranges that stellar collapse struggles to produce? This is where gravitational wave astronomy becomes relevant, because it measures black hole masses directly through merger signals. If a population shows up with unexpected patterns, it can motivate a closer look at non-stellar origins. Another clue could come from how early such black holes might appear. A primordial origin would place them in the universe before the first stars, so they could, in principle, influence later structure formation by acting as double-us. Early seeds of gravitational attraction. The key is not to assume every heavy black hole must have a stellar parent. In this scenario, some could be ancient arrivals, already present before the first starlight, waiting in the dark for the universe to grow around them. Primordial black holes are a possible dark matter candidate. Dark matter is known through gravity, not through light. So compact dark objects are an obvious idea to test. A primordial black hole is dark by nature and massive by definition, which seems to fit the basic requirement. If enough existed, they could contribute to the unseen mass that holds galaxies together and shapes cosmic structure. The challenge is that dark matter also behaves smoothly on large scales, while black holes are clumpy objects. Too many in the wrong mass range would produce effects we would notice, like too many lensing events, disrupted star clusters, or altered galaxy dynamics. So the idea lives in specific allowed windows, where there could be enough mass in black holes without breaking other observations. This makes the hypothesis exciting and fragile at the same time. A single good detection of the right kind of lensing event would be suggestive, but it would not settle everything. Dark matter is a global problem, so any candidate must pass many independent tests. Primordial black holes remain in the conversation because they are simple, physical, and tied to early universe conditions we already know were extreme. No clear evidence for them has been found. This is not for lack of effort. Scientists have searched for their signatures through micro-lensing surveys, through the stability of star clusters, through cosmic background radiation, and through the statistics of black hole masses and mergers. Each method rules out some possibilities and leaves others still open. That is how the field makes progress. The absence of clear evidence means we do not get to claim a neat solution to dark matter or early universe mysteries yet. It also means the universe is placing constraints on how lumpy the early cosmos could have been on very small scales. In a way, every non-detection is still information about the Big Bang's aftermath. The situation also keeps researchers honest about what would count as proof. A single odd event is rarely enough. The strongest case would come from patterns that repeat, from multiple surveys, and from signals that agree across different wavelengths and techniques. Until then, primordial black holes remain a carefully bounded possibility, not a confirmed population. Studying black holes helps test fundamental physics. Many areas of physics can be tested in laboratories, but black holes create conditions we cannot reproduce. They combine strong gravity, rapid motion, and extreme densities in one place. That makes them excellent stress tests for our theories. When scientists compare real observations to precise predictions, they can look for tiny mismatches that might signal new physics. Imaging the region near an event horizon tests how light moves through curved spacetime. Gravitational wave signals test how gravity behaves in violent, rapidly changing fields. High-energy radiation from accreting systems tests plasma behavior under intense gravitational and magnetic forces. These are not separate topics. They are different windows onto the same extreme environment. Black holes also force theorists to confront deeper issues like the connection between entropy and geometry and the fate of information in a quantum BT universe. Even when answers are uncertain, the questions are sharpened by contact with real data. That combination of theory pressure and observational access is rare, and it is why black holes keep showing up at the center of fundamental debates. They connect gravity, space, time, and quantum theory. Black holes are where the big ideas collide. Gravity dominates the motion of matter and light near them, which makes space-time geometry the main actor. Time behaves differently in strong gravity, which makes black holes a natural place to test relativity's view of clocks and causality. Quantum theory enters through predictions like Hawking radiation and through the thermodynamic behavior of horizons. Entropy, temperature, and information become part of the story, even though those concepts feel far from astrophysics at first. The connection is not cosmetic. It shows up as real mathematical relationships, such as the way horizon area relates to entropy, and the way quantum fields behave near a horizon. This is why black holes are often described as bridges between disciplines. They force the universe's largest structures to speak the same language as its smallest rules. If a complete theory of quantum gravity exists, black holes are one of the places where its fingerprints should appear most clearly. They are not just objects in space. They are meeting points for the foundations of physics. Black holes act as natural laboratories for extreme conditions. A laboratory is a place where you vary conditions and measure outcomes. With black holes, nature does the varying for you across the universe. Some systems are quiet and low density, which lets you study subtle gravitational effects without a blinding glare. Others are actively accreting, which lets you study hot plasma, magnetic turbulence, and rapid variability. Some are small, some are supermassive, and that changes how tidal forces behave and how fast processes unfold. Some sit in dense stellar clusters, some sit in galactic centers, and that changes how companions and gas are supplied. Each system becomes a different experiment, run under different boundary conditions. Astronomers then compare them, looking for patterns that reveal the underlying rules. This is especially useful when you want to test physics that cannot be created on Earth. No machine can generate a stable event horizon. No experiment can compress mass into such compactness. Yet the universe provides examples, and it provides multiple ways to observe them, from radio light to X-rays to spacetime waves. That is what makes the field so productive. Time passes more slowly near a black hole than far away. This effect is a direct consequence of how gravity shapes spacetime. A clock closer to a massive object ticks differently from a clock far from it. Near a black hole, the difference can become dramatic. If you could hover near the horizon of a large black hole, your clock would tick more slowly compared with a distant observer's clock. Signals you send outward would be stretched to lower frequencies, and the outside world's processes would appear sped up from your perspective, depending on how you observe them. This is not science fiction. It is a real prediction of general relativity. The reason black holes matter here is scale. Around Earth, the effect exists but is small, which is why it is corrected for in satellite navigation. Near a black hole, the same rule becomes an extreme case, large enough to shape what we observe from accreting matter and from stars on tight orbits. Time itself becomes part of the observable environment. This effect is predicted by general relativity. Einstein's theory replaced the idea of gravity as a force with gravity as curvature. Once you accept that, time is no longer universal. The rate at which time passes depends on where you are in a gravitational field and how you are moving. This has been tested many times in weaker fields, including precise clock comparisons and satellite systems. Black holes extend the same framework into its strongest domain, where curvature becomes intense and where time dilation is no longer a tiny correction. The prediction is not an optional add-on. It is built into the geometry of the theory. In black hole systems, time dilation helps explain why signals from deep in the gravitational well are shifted and delayed, and why the inner regions of accretion flows show distinctive relativistic signatures. It also shapes how we interpret the timing of events near the horizon, because what looks fast locally can look slowed down to faraway observers. Understanding this effect is essential to reading black hole data correctly. It is not a poetic idea. It is a practical tool for turning observations into physical parameters. The stronger the gravity, the slower time moves. This is the simple rule that makes gravity feel like more than weight. In everyday life, gravity is something you feel in your muscles. In relativity, gravity is also something that reshapes the flow of time. Stronger gravity means deeper curvature, and deeper curvature means a greater difference between local time and distant time. The rule has a real, measurable consequence. If you place two identical clocks at different gravitational potentials, they will disagree, even if they started synchronized. On Earth, the differences are tiny. Near a neutron star, they would be substantial. Near a black hole, they can become extreme. This is why the region near a black hole is so informative. It pushes a clean principle into a range where its effects can dominate how light and motion appear. It also gives you an intuitive way to picture what accreting matter experiences. As gas falls deeper, it is not only moving faster, it is living in a region where time itself is running differently. That change affects everything from orbital dynamics to the observed rhythm of flickers and flares. Black holes represent the strongest gravity known. Strong gravity does not just mean heavy mass. It means being able to get very close to that mass while it remains compact. A planet can be massive, but you cannot approach its center without hitting solid ground. A star can be more massive, but it has a large radius, that keeps you relatively far from its mass concentration. A black hole places a great deal of mass into a very small region, which allows space-time curvature to become extreme in a region that is still accessible to observation, at least from the outside. That is why black holes are the best places we know to study strong field relativity. They are also why gravitational wave detections were so important, because mergers probe changing strong fields in a way that no steady orbit can. In black hole environments, light paths bend sharply, time dilation becomes intense, and orbital stability changes in distinctive ways. If you want to see what gravity can do at its most dramatic, black holes are the clearest examples nature gives us. Nothing special is felt at the event horizon of large black holes. This is one of the most counterintuitive truths in the subject. The horizon is a crucial boundary for escape and communication, yet it is not a physical surface. For a sufficiently large black hole, the tidal forces at the horizon can be modest. That means an astronaut falling freely could cross the horizon without being torn apart at that moment, and without feeling a sudden shock that announces the crossing. Locally, the laws of physics still look normal in a small region, because relativity says free fall is like weightlessness. The drama is not in the sensation. The drama is in the global consequence. Once past that boundary, signals can no longer reach the outside world. This is a powerful reminder that black holes are not defined by what they feel like up close, but by what they do to causal structure. The horizon is a geometric feature, not a wall you bump into. An observer falling in would notice no sudden boundary. For someone in freefall, the surroundings change continuously. Starlight ahead becomes distorted and focused, and the sky can appear warped by lensing. The unfailing observer might see the outside universe concentrated into a smaller region of the sky, depending on the path and the black hole's spin. Yet there is no bright line painted in space that says horizon here. The reason is that the horizon is defined by escape paths to infinity, which is a global concept. A person crossing it is making a local measurement, and local physics cannot directly label that global boundary. This is one of the reasons the horizon is so philosophically and scientifically rich. It divides what can influence what, yet it does so without a physical marker you can touch. The experience becomes a lesson in relativity's viewpoint. What you can say about crossing depends on who is measuring, what they can observe, and how their information is limited. That mismatch between local experience and global consequence is central to many black hole puzzles. Outside observers never see objects fully cross the horizon. From far away, the light from an infilling object takes longer and longer to reach you as it comes closer to the horizon. Each successive signal is delayed more than the last. At the same time, the light is shifted to lower and lower frequencies, and it becomes fainter. The result is that the object appears to slow down and fade, as if it is freezing at the edge. In practice, it quickly becomes too dim to detect. This does not mean the object never crosses. It means the information about the crossing is not delivered to distant observers in a finite, easily observed way. This difference between what the falling object experiences and what the distant observer can receive is a key feature of horizon physics. It shapes how we talk about black hole growth and about what can be confirmed observationally. It also explains why horizons are compatible with a universe where causality matters. The horizon hides events not by a curtain, but by the structure of space-time timing itself. Black holes challenge intuition, but follow precise physical laws. They sound like violations of common sense, yet they are among the most rule-bound objects in astrophysics. Orbital motion near them can be predicted. Light bending can be calculated. Merger waveforms can be modeled with remarkable accuracy. The weirdness comes from the laws, not from breaking them. That is why black holes are such powerful teaching objects. They force you to update intuition to match reality, rather than the other way around. They also reward careful thinking, because small conceptual mistakes lead to big misunderstandings, like the idea that black holes constantly suck everything nearby. In reality, you can compute stable orbits, energy extraction possibilities, and signal delays from first principles. When observations match those predictions, it is not just satisfying. It is a deep confirmation that the universe is consistent, even in its most extreme corners. The challenge is psychological, not mathematical. Your everyday experience did not evolve to handle curved spacetime. Black holes make you learn a new kind of common sense. They are simpler than stars, yet far more extreme. A star is complicated. It has layers, chemistry, convection, magnetic cycles, winds, and changing fusion processes. A black hole, once settled, can be described with a small set of properties, and that makes it deceptively simple. Yet the simplicity hides extremity. The compactness creates enormous curvature. The horizon creates a one-way boundary for information. The inner orbits allow matter to reach tremendous speeds and temperatures before disappearing. So you get an object that is mathematically spare, but physically intense. This is why black holes are so valuable in theoretical work. Fewer features mean fewer distractions, which means cleaner tests of ideas about gravity, thermodynamics, and quantum behavior. In observation, the contrast is just as striking. A star shines because of internal processes. A black hole's most dramatic light comes from the space around it, from matter being accelerated and heated by gravity. That makes the environment spectacular, even though the central object remains dark. The simplest description in astrophysics produces some of the most extreme phenomena we know. Black holes remain one of the most important objects in modern science. They influence astronomy, but they also influence physics at a foundational level. In astrophysics, they help explain quasars, jets, galaxy evolution, and the most energetic events we can detect. In relativity, they provide strong field tests that push the theory far beyond the solar system. In quantum theory, they raise questions about entropy, temperature, and information that do not appear so sharply anywhere else. In cosmology, they connect to the early universe through ideas like primordial formation and the growth of structure. Few subjects touch so many areas at once. They also drive new technology. Global telescope arrays were built to image horizons. Kilometer-scale interferometers were built to detect space-time waves. Data analysis methods were developed to pull faint patterns out of noise. Black holes do not just sit in the universe. They shape how we study the universe, and they keep forcing new tools, new observations, and new theories. That is why they keep their central place, even after decades of progress. As we come to the end of our journey through black holes, you have moved through a universe where gravity can shape everything. You have visited the edge where escape ends, the regions where hot matter spirals and blazes, and the quiet places where invisible mass is known only by the motion it commands. You have heard how black holes can collide and send ripples through space-time, how they can power jets that cut across galaxies, and how their influence can reach far beyond the darkness at their center. Along the way, the story widened. It touched the early universe and the possibility of ancient black holes born from the first density waves. It brushed against wormholes and white holes as ideas that test what space-time might allow. It returned to the sky we can observe, to rings of light around shadows, and to the careful measurements that let us learn from things we cannot see directly. Now, let the scale of it all drift outward. Picture distant galaxies as soft lights scattered across a deep black ocean. Picture gravity as a slow, steady sculptor, shaping orbits, shaping time, shaping the paths of light itself. The universe keeps moving, but you do not need to. If you enjoyed this sleepy science journey, you might like to tap like or subscribe, or leave a comment with the part that surprised you most. It helps the channel reach more curious minds, and it supports these long night voyages. And if you are still awake, there will be another video waiting on screen, ready to carry you onward into a new corner of science. For now, let your breathing settle into a calm rhythm. Let your jaw unclench and let your shoulders drop. The night is still here with you, and the universe can keep its mysteries for tomorrow. Sleep well, and good night.